Okay, and now we can welcome to the stage the third speaker, which is Yi-Kai Lin. He's a research scientist and tech lead in network routing at Meta. He obtained a PhD from University of Michigan working on SDN, and is basically leading Meta's data center routing solutions, and his team is actively hiring. So if you're looking for a job, feel free to reach him out. The stage is yours.
Thanks for the introduction. Good afternoon, everyone. I'm Yi-Kai Lin, a research scientist at Meta. And I'm excited today to share our work on Centralium, a hybrid route planning framework for large-scale data center network migrations. Centralium has been deployed in Meta's data centers for years, managing hundreds of thousands of switches globally, fundamentally changing how we approach network migrations, achieving both speed and safety. In this talk, I will walk you through the unique challenges we faced with BGP in large-scale data center migrations, our novel solution that addresses these problems elegantly, and the real-world impact we've achieved in production. Let me start with a quick introduction of the characteristics of Meta's data center networks. First, multi-layer class topology, where there are multiple parallel paths between layers. We employ ECMP to distribute traffic evenly across the available paths. Second, we rely on BGP for our production traffic. We share our experience running BGP at scale in our previous NSCI paper. And overall, it's been a success story. BGP offers flexible policy control over our multi-layer class topology. And its distributed nature means each switch makes independent routing decisions based on local information, which provides excellent fault tolerance and scalability. Third, heterogeneity across data centers. We are constantly evolving our data center designs to adapt to changing demands such as AI training. Shown here is one classic flavor of our DCN topologies. At our scale and pace of change, network migrations become a norm. Let me elaborate in the next slide. We define network migrations as operations that involve changing of network's physical infrastructure, such as adding, removing, swapping switches or circuits, or its configurations, both of which can disrupt traffic. We perform network migrations for many reasons, such as introducing new topologies, upgrading hardware, expanding capacity, and evolving routing designs. To support billions of users and to accommodate the increasing demand of AI training, our data center networks undergo migrations very frequently. Our scale alone makes these migrations non-trivial, as each operation can involve hundreds to tens of thousands of switches and can span weeks to months. Adding on top of these challenges is the constraint to perform these migrations live, meaning we cannot simply drain user traffic off of entire data centers just to perform these migrations, because it will result in significant capacity loss and service disruption. Instead, we must perform these migrations live, maintaining traffic flow, while incrementally transforming the network topology or routing configurations. And that brings us to the key insight of this work. We discovered through experience that distributed routing protocols like BGP have fundamental limitations in supporting these live network migrations. In some scenarios, it can lead to severe traffic disruption that makes the operation simply infeasible. In the next two slides, I will show you two concrete examples from production for the first two problems. And you can find more in our paper, particularly for the transient forwarding state exhaustion. You'll see answers for why we decided not to run unequal cost multipath natively in BGP in our production network. Consider this topology evolution scenario where we're replacing two layers of switches with one new layer with higher capacity. In this example, Perfect's announcement is southbound and traffic is northbound. To perform this migration without traffic disruption, we must introduce new devices before removing the old ones. And as you can imagine, the introduction of physical devices is incremental. Here's where BGP breaks down. The new paths through the new devices have a shorter AS path length. And because BGP prefers shorter AS paths, the first new device will attract all northbound traffic from the downstream devices. This creates what we call the first router problem. A naive solution is to modify the AS path attribute by, for example, prepending a dummy AS number on the new paths, such that both sets of old and new paths are equally preferred. This type of BGP attribute manipulation creates its own problems because these temporary policies must be cleaned up after the migration. But removing them can cause another first router problem because traffic will funnel onto the first path without the prepended AS number. The opposite of the first router problem is the last router problem. In this example, we are decommissioning a slice of full match devices across 2 layers to free up ports of neighboring layers to connect new devices. To perform this migration without traffic disruption, we need to first drain all the devices in this slice to stop both the northbound and southbound traffic, then remove the devices safely. When we drain the devices for removal, the asynchronous nature of BGP convergence means some switches will lose their next hubs before others. The remaining few switches attract all traffic until they too are drained, causing congestion and packet loss. As shown in this figure, whichever layer we drain first, there is a possibility of funneling of either northbound or southbound traffic. The first takeaway of this talk is that fundamentally BGP is not able to encode sequential or spatial conditions. It makes instantaneous local decisions based on current attributes on a per route basis. Live network migrations, however, require conditional logic, such as if the network is in this particular state, apply this routing behavior across all routes. This is where native BGP falls short because they don't have a holistic view of the network. To address this, we developed the routing plan abstraction, or RPA. RPA introduces match action style programmability in BGP, allowing external entities such as centralized controllers to influence routing behavior through conditional actions. RPA integrates into BGP's workflow through 3 key primitives. And let me go through them using the augmented BGP workflow shown here. We'll focus on the ingress pipeline. Say we have a new prefix announcement from 2 peers. This prefix first goes through BGP ingress policy and sanity checks to prevent routing loops. If accepted, it will encounter rel filter RPA, which enforces a fine-grained prefix allow list. Rel filter RPA provides a more direct and flexible way of controlling prefix propagation in our networks to protect different network domains. After rel filter, the prefix will enter the RIB, where route computation happens. Normally, BGP has its own path selection algorithm, where it traverses different BGP attributes and select paths that are equally preferred for forwarding. Path selection RPA can override this algorithm with an ordered list of custom criteria based on standard BGP attributes. Path selection RPA also supports minimum next hop, a protection mechanism that invalidates a prefix with insufficient next hops. The selected paths are then subject to the route attribute RPA, which override their attributes, most typically their weights, for the purpose of traffic engineering. And that's why we don't run native UCMP anymore. The modified path set is then programmed to fit. The beauty of RPA is that it enables centralized route planning with distributed enforcement. BGP switches still make instantaneous local decisions based on current attributes, but the decision criteria is now programmable. With a centralized controller, we can ensure that different BGP switches act consistently in accordance with a globally optimal routing plan. To make RPA instrumental in production, we developed Centralium, a system combining centralized route planning with distributed route enforcement. The Centralium controller performs route planning as well as network telemetry. But unlike a typical SDN controller, it does not compute the routing table. The controller consists of 3 layers: application layer, which implements business logic and generates intended network state in the form of RPAs; the storage layer, which hosts our network state database, or NSDB, and a memory database that hosts current and intended network states, serving as a data hub for other services; and the I/O layer, which performs continuous switch state collection and RPA injection. Centralium allows us to precisely control what RPA to inject, where to inject them, and in what order. In the interest of time, I will not go into implementation details. Please check them out along with evaluation results in our paper. Next, let me show how Centralium trivially solves our previous problems. If you recall in the first example, we ran into a first router problem because we're trying to replace 2 device layers with 1, and BGP prefers the shorter paths. But we want BGP to instead select paths carrying the backbone AS number, regardless of their AS path length. This simple RPA achieves exactly that. What it captures is, first, overwrite path selection for backbone prefaces, and second, select paths with AS path attribute starting with the backbone AS number. Before migration, we pre-install this RPA on all downstream devices. What it does is it will bypass the native path selection algorithm in BGP RIP, so that when paths are being selected, they use our own criteria. During migration, despite AS path differences, BGP selects both old and new paths for forwarding, thus completely eliminating the risk of funneling. This significantly simplifies the operation, as now you can add the new devices one by one at your own pace. It's also worth noting that RPA only needs to be installed once by Centralium before the migration. And because there's no AS path discrepancy before the migration, the RPA injection itself is a no-op to the network. In the second example, BGP ran into a last router problem because it has no concept of safe next hop count. It simply selects whatever is available for forwarding. Its desired behavior, however, is to continue forwarding until next hops drop below a safe threshold, then withdraw the prefaces to stop incoming traffic while keeping existing flows alive. This RPA implements exactly that. We tell BGP, first, select paths normally, but reject the results if the path count is lower than the threshold. Second, keep forwarding entries for the in-flight packets. This is what it looks like in BGP RIP, where native path selection happens regularly, but path selection RPA can overwrite the end results. With this RPA, our migration can be simplified as pre-install RPA on one layer, say the lower layer, then remove the upper layer incrementally. The RPA will kick in at some point and safely drain the northbound traffic. After the upper layer is fully drained, we can simply remove the lower layer in one go. Again, because there are sufficient next hops before the migration happened, the RPA won't change the existing routing behavior when it's being injected. The second takeaway from this talk is that RPA is a powerful abstraction that enables direct prescription of custom routing intent in BGP control plane with backward compatibility. Centralium takes this further by using a centralized controller to perform route planning and on-demand RPA injection, while still relying on BGP for route computation and dissemination. Centralium has significantly changed and transformed our network operations, achieving both speed and safety, which are typically competing objectives at our scale. The key win is migration simplification. In this table, we show a few common categories of network migrations that we perform regularly. Many of them took months to complete prior to Centralium. Now they take weeks or even days. This stems from fewer required steps and reduced BGP config changes, which deploy much slower than RPAs. There are many other applications of Centralium leveraging different RPA primitives that collectively enhance our data center efficiency and reliability. Operating Centralium has reviewed important challenges. System complexity, to begin with, is significant. While the controller alone is arguably simpler than those of full SDN deployments, because the controller is not really computing the routing table, the combined controller BGP system is complex with intricate binary and configuration dependencies. RPA behavior can also be difficult to reason about, especially when RPAs don't immediately change routing behavior when they are installed, which was the case in our case studies. Operators need to carefully define those RPAs and validate them properly prior to the migration. Before I conclude my talk, I would like to share the last takeaway, which contains a few interesting follow-up topics. First is on automatic RPA generation, based on a migration plan and high-level routing intent. Today, operators rely heavily on their domain knowledge in RPA generation. Second is on visibility and debuggability of RPA. How do we reason about the network behavior when different RPAs are selectively injected on different switches? Third is the application of RPA in other networks, such as ISP. Relying heavily on BGP, we believe RPA can help them simplify their migrations as well, as it did ours. But more importantly, we believe RPA can help simplify their steady-state routing configurations. Thank you for your attention. I'm happy to take questions.
Thank you. Any question?
Thanks for your nice talk. You just mentioned that Meta has many data centers and they are connected. So I'm curious, do you have any applications that run cross data centers? For example, large-scale AI training?
Sorry, could you?
You mentioned that Meta has multiple data centers which are connected actually. So I'm curious, do you have currently any applications that run cross data centers?
When you mean run across data centers, do you mean like data flow between data centers?
Yeah. Between from a data center to another data center?
Yes.
Can you share what kind of application?
Well, first of all, for AI training, obviously you have cross data center traffic. But usually we deploy our data centers in different metros, where each metro has has a number of data centers. So you can have server-to-server traffic that crosses from one data center to another. But typically there will be north-south traffic as the user traffic comes in, right, and talk to the servers, and you have server-to-server communications. It could be like storage or a lot of different internal applications.
Okay, that's very interesting. Do you encounter some technical challenge when support this kind of cross data center applications?
I mean, low imbalance would be one, where we probably need to consider traffic engineering solutions. But because of the limitations of BGP, as I described, we have to rely on centralized solutions, which is Centralium. But there are other challenges as well. I think we can go more into details offline, in the interest.
Okay, I see. Thanks.
Any other question?
So, first of all, thank you for the interesting talk. It's always nice to say what happens in a very big environment. So, if I understand well, you started developing this RPA for live migration, no? But do you think that this technique can also be applied to other, I don't know, to face some failure or to add some specific routing strategies, routing policy that is related to whatever, security, segregation, fault tolerance, or things like that?
Sorry, I didn't quite get your question.
So the question is, your technique is mainly related to live migration, no?
Oh.
Let's say live migration, sorry, to modification of the network topology. But do you think that the same approach can be used also to other networking tasks? For example, I don't know.
I see. Yeah, so I think more generally, the concept of RPA, not this specific implementation, but the concept of RPA, I think, can be applied to other use cases. More generally, I think RPA is a powerful abstraction that allows you to sort of incorporate centralized control into a distributed protocol stack.
Then, thank you very much.